This is paper 1-2 from June 2023. In the first question, we are given the equation for dy by dx as 4 over x minus 3 whole cube, and the curve passes to the point 4, 5. We need to find the equation of the curve. So since we have dy by dx, we'll be integrating this equation to find the value of y and the equation for y. We bring x minus 3 power 3 to the numerator. We add plus 1 to the power and divide it by the new power. And since there are no limits over here, we add a plus c to it. Now to find the value of c over here, we use the given coordinate 4, 5. C comes out to be 7. So the equation for this curve would be y is equal to minus 2 over x minus 3 whole square plus 7. In question 2, we're given an expansion x plus a power 6. The coefficient of x4 is p and the coefficient of x squared in another expansion is ax plus 3 power 4 is q. And we're given that p plus q is 276. Okay, so we need the x power 4 term in this. So if we convert this into a plus x power 6, there's no change in the expansion. So we'll find the term 6c4. And this should be equal to px power 4. Six c4 comes out to be 15 multiplied by a squared is equal to p. And then for the other expansion, we have ax plus 3 power 4. We can write it down as 3 plus ax power 4. We need the coefficient of x squared, so we'll find the term 4c2. 3 squared and ax squared is equal to qx squared. This gives us 54a squared is equal to q. Both the x squares on both sides get cancelled out. So we have these two equations now. And we have p plus q is equal to 276. (15a squared plus 54a squared is equal to 276. 69a squared is equal to 276. A squared is equal to 4. A is equal to plus minus 2. We're given the quadratic 4x squared minus 24x plus p, and we need to apply the completing square on it. This would give us, we'll take 4 common from the first two terms. And leave the p outside. We have the square of the first term. We'll take minus 2 outside. We have a over here. So our b should be the value which we multiply with minus 2 to get minus 6x, which in this case would be 3. And to complete the square, I should have a square minus 2ab plus b square, right? But we don't have the term b square over here in this bracket. So what I'll do is I'll add a b square and I'll subtract a b square. So there is no net effect on my equation. And I have the plus p outside. Now these three terms can be completed into a square bracket. Now I need to take this minus 9 outside the bracket, so I'll multiply this with 4 and take it outside the bracket. And this would be our final answer. Now we need to give c in terms of the constant p. So c is equal to minus 36 plus p. Now in part B, we need to find the set of values of p for which the equation has no real roots. B square minus 4ac less than 0. Okay, so since this is a positive quadratic, let's draw a diagram to understand the question over here. We have a U-shaped graph. And the turning point here would be, let's say, 3 and p minus 36. So right now, this quadratic probably has 2 roots. However, if it moves above the x-axis, which is y is equal to 0 over here, it would look something like this. So there are no solutions with the x-axis over here. And to have this graph in this shape, we need to move it above the x-axis, which means that this coordinate of the turning point, the y-coordinate, p minus 36, should be greater than 0. So the turning point of this graph should have the y-coordinate greater than 0. P minus 36 should be greater than 0, which means P is greater than 36. Now, whenever P would have a value greater than 36, this equation would have no real solutions. In question 4, we have 8x power 6 plus 215x cubed minus 27 is equal to 0. To make this easier for us, we can use a substitution. Y is equal to x cubed. This gives us 8y squared plus 215y minus 27 is equal to 0. So when we middle term break this, we'll get these are the two factors, y plus 27 and 8y minus 1 is equal to 0. Now, when we find the values for y, we'll get y is equal to minus 27 and y is equal to 1 over 8. We substitute x cubed back in place of y. So the values for x cubed are minus 27 and 1 over 8. The values for x should be minus 3 and 1 over 2. In question 5, we need to find the area for the shaded region. We have the limits 0 and 4, and we're given the equation of the curve. To integrate, we'll add 1 to the power. This becomes 3 over 2, and we'll divide by the new power. We'll do the same thing here. We'll add 1 to the power. This becomes 5 over 2, and we'll divide by the new power. Five over 2 divided by 5 over 2 gets cancelled out. So we have x power 5 over 2 remaining over here. Now we'll plug in the limits. So we'll plug in the upper limit. And we'll subtract the value we get when we plug in the lower limit. the answer comes out to be 64/3, which can be written as 21 whole 2/3 for the area. In question 6, we're given a diagram with the sector OAB, in which O is the center and OA would be the radius. Since these two sides are equal, these two angles would be equal as well. For part A, we need to show that the arc length is 2x theta cos theta. So we need to find the value for the radius. Now we can use cosine rule for this. If I take the side AP as the side C and use the angle theta and the side's radius in x, I can use cosine rule. X square is equal to r square plus x square minus 2rx cos theta. These two x squares get cancelled out. So I'm left with r square is equal to 2rx cos theta. R comes out to be 2x cos theta. Now the formula for the arc length is S is equal to r theta. So S is equal to 2x theta cos theta. Now in part B, we need to find the area of the shaded region, APB, in terms of x and theta. So we'll subtract the triangle OAP from the sector OAB. Area of sector minus area of triangle. Half r square theta minus half AB sine C. We have the radius as 2x cos theta. And the area for the triangle would be half times x times 2x cos theta multiplied by sine theta, which is the angle between the radius and the side OP. When we simplify this, we'll get 4x square cos theta upon 2. So we can simplify it to 2x square theta cos theta minus x square cos theta sine theta. We can also take x square cos theta common outside, giving us 2 theta cos theta minus sine theta. In question 7, we need to expand cos theta plus sin theta whole square. So this gives us now we know that cos square plus sin square is equal to 1. So we can write it down as 2 sin theta cos theta plus 1 is equal to 1. These two ones get cancelled out. So we have 2 sin theta cos theta is equal to 0. Now we can equate sin theta with 0 and cos theta with 0 as well. Sin theta equal to 0 would have the values 0 and pi, and cos theta would have the value pi over 2. The values are 0, pi over 2, and pi. In part 2, we need to verify that the only solution of the equation cos theta plus sin theta is equal to 1 or 0 and half pi. So when we plug in 0 in place of theta, we'll get 1 plus 0, which is equal to 1. So 0 is the solution for this. When we plug in half pi in this, we'll get 0 plus 1, which is also equal to 1. But when we plug in pi in this, we'll get cos pi plus sin pi. This would be minus 1 plus 1, which does not equal to 0. Hence, 0 and pi over 2 are the only two solutions. Now in part B, we need to prove this identity. So what I can do is I can take the LCM over here for the first two terms. So sin theta multiplied by cos theta minus sin theta plus 1 minus cos theta multiplied by cos theta plus sin theta. And we'll multiply the denominators. The numerator expands to sin theta cos theta minus sin square theta plus cos theta plus sin theta minus cos square theta minus cos theta sin theta. And when we expand the denominator, we get cos square theta minus sin square theta. We have a sin theta cos theta and a minus cos theta sin theta, which get cancelled out with each other. We have a minus sin square and a minus cos square, and they add up to minus 1. We have minus 1 plus sin theta plus cos theta. Now in the denominator, we can replace cos square theta with 1 minus sin square. So this becomes 1 minus 2 sine squared theta. Now in part C, using the results from A part 2 and B, we need to solve the equation sine theta over cos theta plus sine theta plus 1 minus cos theta over cos theta minus sine theta is equal to 2 cos theta plus sine theta minus 1. So we can use the identity over here to replace these two fractions. We can see that these two sides can be cancelled out. This whole bracket is cancelled out by these three terms. And then we have, when we cross multiply, we get 1 over 2 is equal to 1 minus 2 sine squared theta after cross multiplication. 2 sine squared theta comes out to be half. Sine squared theta is 1 over 4. Sine theta is equal to plus minus 1 over 2. The basic angle over here would be pi over 6. We plot the angles in the first two quadrants where sine is positive. Since we only have the given domain as 0 till pi for theta, theta has the values pi over 6 and 5 pi over 6. However, we'll need to remember that when we had this initial equation, the numerators on both sides can also be 0 and the equation would be balanced. And cos theta plus sine theta is equal to 1 would have the same solutions as these two numerators, and the solutions were 0 and half pi. So the values for theta would also be 0 and half pi. This would be the answer. Moving on to question 8, in part A, we need to sketch the graph of the inverse. So we know that the inverse is a reflection in the line y is equal to x. This is the line y is equal to x. Now I can see that this point, on this point we have the x0 and y is slightly less than pi. So the reflection would be a point over here, where x would be a point slightly less than pi and y would be 0. This point would be the same. So now this point is 2 pi comma 3 pi over 2. So we'll have 3 pi over 2 comma 2 pi as well. The y is equal to x line should be passing through pi pi and 2 pi comma 2 pi. This would be our curve for f inverse x. This point would be slightly to the right. This would be our curve f inverse x. In part B, we need to find the expression for f inverse. Y is equal to 3 plus 2 sine 1 over 4x, and we need to make x the subject in this equation now. We take 3 to the other side, it becomes y minus 3 is equal to 2 sine 1 over 4x. We divide 2 to the other side, so we get y minus 3 over 2 is equal to sine 1 over 4x. Then we apply sine inverse on this. We multiply 4 to the left-hand side, so we get 4 sine. And now we also change the symbols. So this becomes x minus 3 over 2. And this is equal to f inverse of x. In part C, we need to complete the sketch of the curve. We're given the graph for 0 to 2 pi. We need to sketch it for 0 to minus 2 pi. We can take the values for x is equal to minus pi and minus 2 pi. This would be the completed graph. We need to see if this graph would have an inverse. So you can see that the inverse would exist for the given domain. Because it is a one-to-one function. And it will pass the horizontal line test. In part D, we need to describe the transformation in the right sequence, which transforms sine x to the graph of y is equal to fx. So we are starting from sine x, and we need to transform this into 3 plus 2 sine x, the angle 1 over 4x. So the first change would be in the x-axis, a stretch of scale factor 4. In the x direction, then we're multiplying the equation by 2. This means a stretch of factor 2 in the y direction. And then we're adding a 3 to it. For the y values. So there's a translation or a shift of 0, 3 vector. So 3 units in the y direction. Moving on to question 9, we have the second term of a geometric progression given as 16 and the sum to infinity as 100. So T2 can be written as A multiplied by the common ratio, which is 16. And the sum to infinity has the formula A over 1 minus R, which has the value 100. AR is equal to 16 and A is equal to 100 times 1 minus R. We substitute the value for A from the second equation back into the first equation. We get 100 times 1 minus R multiplied by R is equal to 16. R minus R squared is equal to 16 over 100 r square minus r plus 4 over 25 is equal to 0. This can be factorized to 5r minus 2. No. We need to apply middle term breaking to this. When we factorize this, we get 5r minus 1 and 5r minus 4 is equal to 0. R has the values 1 over 5 and 4 over 5. And A has the values 80 and 20 from the first equation. In part B, we need to show that the nth term of one of the two possible geometric position progressions is equal to 4 power n minus 2 multiplied by the nth term of the other geometric progression. So we have r as 1 over 5 when a is equal to 80, and r as 4 over 5 when the other a is equal to 20. The formula for this would be when I split the powers, I get 1 over 5 power n multiplied by 1 over 5 power minus 1. This can be written as we'll do the same thing over here. Four over 5 power n minus 1. So we split the two powers. N minus 1. Tn is equal to 20 times 5 over 4 times 4 over 5n. When we divide these two, we should be getting 4 power n minus 2 These two 5 power n's get cancelled out. And we have 400 over 25 as 16 over 4 minus n. This can be simplified to 4 square is supposed to be plus n. But if we divide 25, 4 power n and 5 power minus n by 400, 5 power minus n, we get 4 power n minus 2. So we have the answer now. In question 10, we have the equation of a circle with x minus a whole square plus y minus 3 whole square is equal to 20. The line y is equal to half x plus 6 is the tangent to the circle at the point P. We have the center as a comma 3. We can draw a tangent over here with if we equate these two equations, we can find the possible coordinates for P over here. I'll substitute half x plus 6 and y over here in this equation. X minus a whole square plus half plus 6 minus 3 would give me 3 is equal to 20. X squared minus 2ax plus a squared plus 1 over 4x squared plus 3x plus 9 is equal to 20. When I add these two brackets, I get 5 over 4x squared plus 3 minus 2ax plus a squared plus 9 minus 20. This is our equation. We need to show that one possible value for a is 4 and we need to find the other possible value. So let's plug in 4 in place of x. I'll need to apply b squared minus 4ac on this. Equate it to 0. B squared over here would be 3 minus 2a whole square minus 4 times 5 over 4, and a squared minus 11 is equal to 0. Now we need to show that at a is equal to 4, we get the answer as 0, sorry. So 3 minus 8 whole square minus 4 times 5 over 4 times 16 minus 11. 25 minus 25 is equal to 0. A is equal to 4 is proven. Now we need to find the other value for a in this. Once we have this value for a as 4, we can use the b squared minus 4ac equation again. Three minus 2a whole square is equal to 5a squared minus 11. Let's expand this bracket as well, so we get minus 4 plus 4a squared minus 12a plus 9. Bringing all the terms together, I get minus a squared minus 12a plus, should have been minus 55. Now when I factorize this quadratic, I'll get a minus 4 and a minus 16 is equal to 0. We already have proven a minus 4, so the other solution for a should be a plus 16. So the other solution would be a is equal to minus 16. For a is equal to 4, we need to find the equation of the normal to the circle at P. Since we have the value for a now, we can find the value for the x coordinate of P, which is the intersection of this tangent and the circle. When we simplify this, we'll get x square minus 4x plus 4 is equal to 0. When we factorize this, we get x minus 2 whole square is equal to 0. So x is equal to 2. And in this equation, when we plug in x is equal to 2, we get y as 7. Y would be 7. This would be the coordinate for P. Now P is 2, 7, and we need to find the equation of the normal. The gradient of the tangent is 1 over 2, so the gradient of the normal should be the negative reciprocal of it. So the gradient of normal over here would be minus 2. Now we can construct the equation. So y minus y1 is equal to m bracket x minus x1. Y minus 7 is equal to 2 bracket x minus 2. We have 2x minus 4 plus 7. Giving us y is equal to 2x plus 3. It should have been minus 2. Minus 2x plus 11. In part C, for a is equal to 4, find the equations of the two tangents to the circle which are parallel to the normal found in B. Okay. Let's draw a diagram again. We have the center as 4, 3. Now the gradient of the normal was minus 2. So the two lines of the tangents should be with the gradient minus 2. These are the two possible lines. This tangent would be perpendicular to the radius or diameter. So if we can find the equation of this diameter, we can find these 2 points. If the tangent has the gradient minus 2, the diameter will have the gradient 1 over 2. So the equation would be y minus 3 is equal to 1 over 2 bracket x minus 4 using the coordinates 4, 3 with the gradient half. Y is equal to half x plus 1 Now we can substitute or simultaneously solve this diameter equation with the circle equation to find these 2 points. When I substitute y in this, I'll get x minus 4 whole square plus half x minus 2 whole square is equal to 20. X square minus 8x plus 16 plus 1 over 4x square minus 2x plus 4 is equal to 20. We cancel out these 20s on both sides. 5 over 4 x square minus 10x is equal to 0. 5x square minus 40x is equal to 0 after taking the LCM. This comes out to be 5x bracket x minus 8 is equal to 0. X has the possible values of 0 and 8. And the subsequent y values would be, when you plug them back into this equation, at 0 I get 1, and at 8 I'll get 5. Now once I have these two equations, these two coordinates, I can find the value for the y-intercept of these two lines. So y is equal to minus 2x plus c. Now once I have these two coordinates, 0, 1 and 8, 5, I can find the value of c by plugging them in. So for 0, 1, c would have the value of 1, and for 8, 5, c would have the value 21. So the equations I get are minus 2x plus 1 and minus 2x plus 21. Question 11 now. So we need to find the dy by dx for the given equation. And k is a positive constant, so dy by dx over here would be k times 1 over 2, 4x plus 1 power minus 1, multiplied by the differential of the bracket, 4, and minus 1 as the differential for x. This simplifies to 2k upon 4x plus 1 minus 1. power should be minus 1 over 2, so this would be under root of 4x plus 1. In part B, we need to find the stationary point in terms of x. So we'll equate dy by dx to 0, since the gradient is 0 at the stationary point. X has the coordinate 4k squared minus 1 over 4. We're given the value in part C for k as 10.5. We need to find the equation of the normal, where the tangent to the curve makes an angle of tan inverse 2 with the positive axis. Let's draw a diagram to understand this question a bit. Let's say, for example, my curve is something like this. And this is the tangent. And the angle it makes with the positive x-axis is tan inverse of 2. Tan inverse tan theta of y over x would give me the angle theta over here. Now we know that y over x gives us the gradient. So if the angle is tan inverse of 2, this means that the gradient is equal to 2 for the tangent. Now the equation for the dy dx of the curve is 2k upon under root 4x plus 1 minus 1 2k upon 4x plus 1 minus 1 is equal to 2. We have k as 10.5. We plug that in over here. So we get 21 is equal to 3 root 4x plus 1. Root 4x plus 1 is equal to 7. We square both sides. We get 4x plus 1 is equal to 49. And we get x as 12 over here. Now with x as 12, we can find the y coordinate using the equation. We'll use this equation with the given k value as 10.5 to find the value of y. We have the y coordinate as 66.5, 12 comma 66.5. 9 Now at this coordinate that we just found, we need to find the equation of the normal. So the tangent had the gradient 2. So the normal would have the gradient of the negative reciprocal of 2, which is minus 1 over 2. And the coordinate 12 and 66.5. Now using these two gradient and the coordinate values, we'll construct the equation. So y minus 66.5 is equal to minus 1 over 2, x minus 12. This would be our equation.